Okay. Today we're going to talk about what we call Riemann sums. Okay. So we have been talking about finding the area between our curve and the x-axis. We've been approximating that using rectangles. Okay. Well, I want you to imagine making our rectangles super duper duper small so that we have a lot of them. Okay, do you agree the more rectangles we have, the more accurate our area would be? Yeah. Okay, so what we're going to do is we're going to make our rectangles smaller and smaller and smaller until we get closer to the actual area under the curve. Okay. Basically, we are going to sum up infinitely many rectangles. Okay? Infinitely many rectangles in a certain space. Okay? Are we okay with that? Okay. All right. Limits, yay! Okay. We are going to find an equation for the sum of n rectangles and then take the limit as we approach infinity. Okay? So this is representing, we are going to add up rectangles. Okay? So the height times our thickness. That's how we found our rectangles, correct? Okay? Well, I want n number of rectangles, so that's why we're summing up from 1 to n. If we take the limit as n approaches infinity, okay, basically we're summing up an infinite number of rectangles. This is what gives us our exact area. So this is the definition of a Riemann sum. Okay, this is kind of, I've already informally talked about this. Okay, don't feel like you need to write everything down on this slide. Okay, I want you to understand what we're doing. Okay, f is a function defined on an interval a to b, including a and b. Okay, what we're going to do is we're going to partition a to b. What does it mean to partition? Okay, we're going to break it up into little pieces, right? So we're going to break it up into n number of pieces, okay, between a and b. All right? The width of our partitions, if you will, okay, will be how far apart these values are, okay? We're going to call it delta x. Okay. And then C is going to be in this subinterval. Okay, this is something we've already looked at. Okay, the Riemann sum then for that partition from 1 to n of the height times the width. Okay. When we take the limit of our rectangles, okay, we have n number of rectangles. If we take the limit towards infinity, okay, we can't really have an infinite number of rectangles, can we? But we can take the limit of an infinite number, right? That's why limits were so important way back in the day, okay? If we can take a limit of infinite number of rectangles, we actually get the exact area. All right? So, here's where the connection comes. A definite integral from A to B. Before Christmas, we talked about indefinite integrals. Okay? A definite integral from A to B is giving us the curve, the area under the curve. So by us finding the area under the curve, that means we are taking the integral from A to B of a function. Okay? You have not seen values right here on your integration sign. Okay? When there are values on your integration sign, that means you are finding the area under the curve from A to B. Now, I am going to teach you how to find the exact area using a Riemann sum. Okay, but first, okay, we're going to talk about some properties with integrals because we kind of already know some of the properties with integrals, so we're just going to buzz through them very quickly. Okay, please keep in mind when you see this, that means find the area under the curve from A to B. Okay, so let's remind ourselves. Well, I guess this one you don't know yet. The integral from A to A. If I'm finding the area under the curve, I start at A and end at A. How much did I calculate? Nothing. So if your definite integral starts and ends at the same place, there is no area. The integral from B to A is the same thing as the negative integral from A to B. If we find area backwards, it's negative. That's what it's saying. If I have the integral from A to C of a function, and I add it to the integral from C to B of the same function, then I can squish them together for the integral of A to B. Okay. Like I said, most of these are common sense, right? Okay, this is something we've seen before. If I have addition or subtraction inside of my integral, we can break it apart to two separate integrals that are being added or subtracted. Okay, and the same thing with a constant. If we have a constant in front of our function in our integral, we can take it outside. You've seen those two before. Now, on our quiz, you had to know some shortcuts, correct, for summations, okay? And you're thinking to yourself, Mrs. Holman, why did I need to know this? Okay. We will now use those to help us, okay? I'm going to give you some shortcuts, but we are going to go through what these shortcuts are. You're going to help me determine why these are the values, okay? So I have the limit as n goes to infinity of 1 over n times the summation from 1 to n of 1. Okay, help me out. What is the summation from 1 to n of 1? N. So this is the limit as n approaches infinity of 1 over n times n. So the limit as n approaches infinity of 1 is 1. Okay? You need to remember that if you have the limit as n approaches infinity of this, it is 1. Next shortcut. The limit as n approaches infinity of 1 over n squared times the sum from k equals 1 to n of k. Okay. So we have the limit of 1 over n squared, the sum from 1 to n of k.
K.
No.
No. Oh God, I'm just.
Okay. So we have the limit as n goes to infinity of n squared plus n all over 2n squared. How do I find the limit towards infinity? We have to look at the
asymptote.
the asymptote. Where's the horizontal asymptote? This limit is 1/2. Okay. Anybody have an idea of what this one would be?
1/4.
No, 1/4.
Oh, I didn't see the
1/8.
Okay, 1 over n cubed, the summation from 1 to n of k squared, right? What's our shortcut for k squared?
N times n plus 1 times 2n plus 1 over 6.
Okay. So where's our horizontal asymptote on this one? 1/3.
And it gets 1/4.
This one is 1/4. You need to know these. And yes, there is a pattern. Right? Do you see the pattern?
No.
You see, it's like
Okay. So what we're going to do we're going to sum up our rectangles and take the limit as n goes to infinity. So we're going to sum up an infinite number of infinitely small rectangles. Okay? So we need to talk about a couple things. Okay? This right here. Okay? Let's talk about what x of k is.
that's whatever the input number is when you plug in.
Okay, we need to find all of our heights, right?
Yeah.
Okay. So where do we start with our heights?
1.
Wherever it's the range starts.
Okay.
Yeah,
So that's our 1.
Okay. So we start at A, right? And then we have to add. How do we find like the next rectangle? we go over
1.
the height or the width, right? This?
Yeah.
Okay. Okay. K is, we start K as 1, right? So this is describing, what I just wrote here is describing a right-hand rectangle, okay? Our interval starts at A, right? And so we're going to use the right-hand side of it. So we're going to add our thickness, okay? So we can plug that in for our height. When I add 2 of our thickness, that's our second rectangle. When I add 3 of our thickness, that's our third rectangle, so on and so forth. Okay, does that make sense? So what we're going to have to do is we're going to have to figure out what x of k is so we can substitute it into our function to get an expression right here. Okay? So we are going to find the area under the curve x squared over the interval, it looks like 0 to 5. Okay? So let's write that as an integral. If I'm finding the area from 0 to 5 under x squared, that means we're taking the integral from 0 to 5 of x squared dx. Which means take the limit as n approaches infinity of the sum k equals 1 to n of f of x of k delta x, right? So first we need delta x. How did we find delta x on our quiz yesterday? What? B minus A over n. And we're going to do n number of rectangles, so we're going to leave it as n. So delta x is 5 over n. Okay. Now we need x of k. Okay. We're doing right endpoints, so we need to start with A, which is 0. And then we are going to add our thickness, however many times to get to that rectangle. Okay. So what do we need to do with x of k? X of k goes in for our function. Right?
Okay.
So, let's see. The integral from 0 to 5 of x squared dx is, we're going to take the limit as n approaches infinity of the sum k equals 1 to n f of x of k. That means we're plugging this in for f. Does that 0 really need to be written? No. So we're taking 5n times k and plugging it in for x squared times delta x. All right, so now let's write this as the limit as n approaches infinity. This, how could I rewrite this? Five squared times 5, 125 over n squared times n, thank you, n cubed times a squared. Okay. Now, we went through those shortcuts for our limits, correct?
We did.
Okay, so what I'm gonna do is I'm gonna say the limit as n approaches infinity of 125 over n cubed times the sum what's the limit as n goes to infinity of the sum from 1 to n of k squared? What was that? 1/3?
Multiply by 125.
What? What?
125. Multiply.
Well, what I'm going to do, yes, you were right. Because we have 125, we need the 1 over n cubed to be with this summation, right? Sorry, I didn't write that out very well. The 1 over n cubed times the summation of k squared, that limit will always be 1/3. And why will that limit always be 1/3?
Because you told us. And we also figured it out using our other.
Okay, if we rewrite this in closed form, right, we're going to get the same limit every time. It's going to simplify to yes.
So is that the area or is it one?
That is the exact area that I have shaded up here.
Well, not exact, but very close.
No, that is the exact. Because we just summed up an infinite number of infinitely small rectangles.
Yeah, but
Since we took the limit of our n rectangles, we basically summed up infinitely.
basically.
Aaron.
We summed up an infinitely small,
Because it's the limit, that's what it's
an infinite number of
You'll
infinitely
always keep
small
adding a
rectangles.
decimal number on at the end, but you're still approaching 23.
Let's do this one.
Around.
No, I'm gonna help you.
Don't scheme it.
What is the interval that we're going to find the area?
-2 to 2.
-2 to 2. Okay. And we're going to find that by taking the limit as n approaches infinity of the sum k equals 1 to n of f of x of k times the thickness. Okay. I want you to kind of notice something here. Notice how we have f of x of k times delta x.
Yeah.
Notice in our integral f of x dx.
Oh, because dx is the change in
You see that?
wow.
Okay.
Well,
Okay, so help me out. What do we need to do first?
find the hypothetical x.
Okay.
Okay, we need delta x. And we find that by taking
A by
b minus a over n. Now we need
Actually,
x of k. Okay, this x of k is going to give us what we actually need to plug in for each height instead of having to write them all out, right?
yeah.
So we start with,
A
which is -2, and then we have to add our thickness over and over and over.
K x or K change in x.
Okay, so our change in x times k. Okay, now before we get into our summation, inside of our summation we need f of x of k.
So to plug
So
for
we plug that in.
That means we have to plug this in to here.
yeah.
Which means we're going to have to be careful with our algebra. Okay. So we have 4 minus the quantity.
Um,
When we take this binomial squared, we first get 4. We're going to take negative 2 times 4 over n times k.
negative 16 over nk. Over n squared k.
Okay, so we're going to take it twice, right? So we're going to take negative 2 times 4 over n times k. So, and we're doing that twice.
So it's
Right.
okay.
So I'm going to write it like this right now. And then plus our last product would be
16 over n squared k squared.
okay. So f of x of k would be 4 minus 4 goes away, correct? Good.
Plus 16.
It would be positive 16.
Minus 16 over n squared k squared.
Okay. So now the integral negative 2 to 2 of 4 minus x squared dx is the limit as n approaches infinity of the sum k equals 1 to n of our function
And
times our thickness. Correct? Huh?
no, it's not supposed to be 1.
I had negative and I made it a positive. Better? Okay. So everyone go on the same page.
Yeah.
All right. So now I'm going to write this as okay, the limit as n approaches infinity of, we have the sum k equals 1 to n of, this becomes, okay, so 16 over n times k times 4 over n would be,
Okay, I have a question.
Yep.
Could you just like put 4 over n outside of that, and then like have the two sums in the middle, and then have the 4 over n to like just distribute afterwards?
you can, and that's kind of what we're going to do right now.
Alright.
All right, I want you to write it like this first.
Yeah.
All right, and now we have 16 times 4, which is
64.
64 over n cubed, squared, Okay, now why did I write it like that?
Because you distributed it first and you separated them with the subtraction.
Okay, well, and 64 over n squared, that is a coefficient,
Yeah.
right? So I can move it out here. Minus the sum k equals 1 to n. This is,
64 over n cubed.
and then we're summing up k squared. So here we go. I have 64 times, what is the limit as n approaches infinity of 1 over n squared times the sum of k? That is 1/2. Minus 64 times 1 over n cubed times the sum of n squared. The limit is 1/3. So we have 32 minus 64 thirds.
Exact area, Aaron.
And what is that exact area, Jared?
32 minus 64 thirds.
Yeah, what is that?
That's the exact area.
32 thirds?
But it can also be written as 32 thirds.
Yeah. Okay. Now, if it makes you feel better, if you want to do the limit, like if you want to put that into closed form and do the limit, If that helps you understand what's going on better, that's fine. Otherwise, you can remember that this is always going to have a limit of 1/2. The 1 over n cubed sum of k squared, that's always going to have a sum of, or a limit of 1/3. Okay? Questions over either of those two examples? Be careful with your algebra. Okay. Well, right now a lot of this is algebra, right? The hard part. Okay. Now let's think calculus-wise. You're gonna have some problems like this. Okay. I am telling you that the integral from 0 to 5 of a function is 10, and the integral from 5 to 7 of the same function is 3.
0 to 7 is 13.
Okay, so the integral from 0 to 7 would be
13?
y.
Because A to C and C to B is the same as if you added them together.
Okay, we can add those two pieces together. We're just adding the areas together, right? What about the integral from 5 to 0? -10. If we do it backwards, it becomes negative. Yes, area, negative. That's okay in calculus. The integral from 5 to 5.
0. Calculus, everything that wasn't allowed is not allowed.
Yeah.
I'm civil engineer.
0, the integral from 0 to 5 of 3 f of x dx.
30. Right, the calculus side of it is much easier. I don't know if it's like I'm paying more attention this semester, but this semester seems to be easier. You get it.
It's because I'm back, right?
Yeah, no, it's not, that's probably a great deal of it.
Right now?
Yeah.
Give me a second. Okay.
I remember taking a concept.
Yeah.
I think it was like, one big thing, essentially we started multiplying.
He's like, what? Too big and oh my god.
I'm allergic to negatives. I'm allergic to negatives.